So thanks for inviting me here. There's a few. I keep tweaking this thing as all the other talks go by. I've been adding and trying to delete some stuff, but hopefully there will be plenty of time for discussion at the end. I always like to begin with my most important slide, is thanking everyone who pays for my time. Protein Structure Initiative being a big part of it until next year. And Tom Albert was my thesis advisor, and he's very sadly passed away earlier this year. But he was the founder of 831 and made my whole career possible. So there's an old saying, because if you don't have good data, you have no data at all. And this is, I've heard attributed to Sung Ho Kim, possibly someone else said it before him. But it really speaks to what it's like to be a scientist. After all, we love good data. We like sharp peaks and straight lines and teeny tiny little error bars. The problem with having data like that is that usually there's somebody else whose lines aren't quite as straight, and whose error bars might be a little bit bigger, who can come to the same conclusion you do before you. That's the problem of signal and noise. And there's a few kinds of errors that we don't normally think about in MX because we've just traditionally dealt with them. And this is something I think that has come up here. This is a calculated electron density map, and you can get them all from my movies page here. This is perfect phases and perfect amplitudes, and I'm just throwing out the top N HKLs with the brightest spots. So let me play that again so you can see. This is the number being thrown out, and then I switch to a percentage in a moment. I'm just rocking the map back and forth to give you a better 3D effect. But those of you who looked at a lot of crappy maps probably recognize some of these features. So you see these kind of tenuously sticking electron density, and it's the scary part of all this is of that last map, the R factor is 0, because all the spots that are missing don't enter into the R factor. But they're the brightest ones, the most important ones, since they have this effect on the electron density of sucking down one part and pushing up another, effectively changing your sigma contour level as you move around the map. So you might be able to get tyrosine rings with less quality data than you would without. This one is completeness with random deletion. There's a lot of complaints about R factors, particularly the R-free, as it takes out 5% of your data. But you can see, you can easily survive 5, 10, even 20% of your data randomly gone. It doesn't really change the map all that much until you start getting to ridiculous levels. This is what an R factor looks like. So this is perfect phases, and I'm changing the amplitudes to be different from the ones that match that model. And if you wait long enough, you start to see a little bit of change, but not much. This is phase bias. Something that I think is perhaps a good question for this group is, what is phase bias? How would you measure it? And who are you going to name the unit after? Because this is now going back to perfect phases and changing the amplitudes to those of a different structure. And you see that, well, you can tell where the atoms in the structure are rather quickly. So this is the figure of merit, which is the cosine of the phase error, and this is the true figure of merit. So I made a lot of these movies actually a long time ago to try and teach myself about the sorts of problems you could run into with data collection back when I was just a young graduate student and didn't know what I was doing. And in a way, I feel like we're all in this boat again. Now that we have this new source with new detectors and everything's new again. So in a way, we kind of have to return to our roots and think about all these problems once again. Because the biggest problem that we have is this one, resolution. Start out at a 1 angstrom map there, which is always nice to have. But you can see that eventually you do in fact expect things, even with perfect amplitudes and perfect phases, at low resolution, things will start to poke out the density. And you end up looking at the kinds of things that Fruits and Kendra were looking at with the very first modular structure, which is just big sausages for Ulysses. So we're all fighting for resolution. I think that in MX is the biggest problem that we face, is how can we get our crystals to track better. So in general, all these are different sources of error. And you have a signal and you have an error. And there really is a scale. There's some projects begin up here when you got great diffraction. It goes to the edge of the detector. All the automated programs work, and they never last very long. You spend very little of your time up here, and most of it down here in the 7th level of hell, trying to claw and scratch and optimize your way until you cross this imaginary barrier that I call the threshold of solvability, where coming to whatever conclusion you want in a statistically defensible way, it goes from being a complete waste of time to being merely painful. And so it's very important to know where that line is, because that's where your competitors are going to cross over at first. So I would amend Sung Ho's statement to say that even if you're a biologist, you do need to learn a little bit about statistics if you want to really be cutting edge with data quality. So I'm going to give you a very brief statistics lesson. And that is 1 plus 1 is 1.4. Now I know this is just pretty late in the day and this isn't what you learned in elementary school, but when it's noise, it really does add as the squares, and 1.4 is square root of 2, more or less. Now the significance of this is that if you have two sources of error in your experiment and they're equal, if you get rid of one of them, or even if you have one source of error, you introduce a new one that's equal to the total noise you already have, it's not twice as bad. It's only 40% worse. And if you're 3 to 1, so you introduce a new source of error that's a third of the total noise, then it's less than 10% different. In fact, you'd probably be hard-pressed to even notice that. We don't actually measure noise power to better than 10% itself. And if it's 10 to 1, it's really impossible. You have to measure the amount of noise accurately to 4 decimal places to prove that this new source of noise even exists. And this is the problem with XFEL data processing, is that there's a million possible sources of error, and only one of them is dominant. All the other ones are smaller than it, even slightly smaller, and you'll never know they're there. So fixing something like, let's say, making the beam more monochromatic might have no effect at all, even though it should have an effect. There's something else getting in the way, preventing you from seeing that effect. So what are the sources of error that we're dealing with? I like to group them in terms of how they depend on time and how they depend on the magnitude of the signal. Photon counting error is the one we're all familiar with, and what we'd like is for it to be the only one. And unfortunately, a lot of simulations, that is the only source of error, is photon counting error. You take the square root of the number of photons, and that's easy to calculate. It's actually the only source of error that is proportional to the square root of the number of photons. Everything else either doesn't depend on it at all, like readout noise, or is proportional to it, like all these fractional errors. I'll give you an example of that. A typical detector calibration error on a synchrotron MX beamline is about 3%. And if there's time, I can go into how you measure that later. But what that means is in order to overcome the 3% error, if you have a bifoot ratio of, say, 1%, then you plug that into this formula, square it, and that's the multiplicity you need of truly independent observations to average out that amount of error. With XFELs, we're dealing with about 100% per spot. So you need to have a true multiplicity, which is quite a bit higher. And the reason why I asked Carl Nass about his multiplicity is because, based on my little formula here, gadolinium lysozyme at the edge has about a 9% bifoot ratio. And based on this equation, you should need a multiplicity of 132. And since you have to measure everything twice with bifoots, 300 is actually about right. So the partiality problem, I think, is the dominant source of error. There's those who don't agree with me, but let me explain to you why I think it is. So you have some spot in reciprocal space, and you don't know if you're measuring it here or here. That therein is really the problem. And you think about the magnitude of this. If you have a 1 micron crystal with no mosaic spread and a perfectly monochromatic beam and all that, the width of this peak is 0.006 degrees, total width. So even a 0.003 degree error can be 50% error. Now, Nick, you've done some runs on my fake data sets. Do you remember what your orientational accuracy was?
Before correction was 1%, 0.1 degree, and then afterward, no, I couldn't spell.
Sorry, I put you on the spot. No, I don't remember. I can but I don't think it was quite this good, or maybe
yeah. Not.
So there's
never got into that issue at all.
Okay. So that's the partiality problem. And I'd like to, if there's anything I could contribute to this meeting, I hope it's a better understanding of partiality and what that is. So I want to begin with everyone's favorite formula in crystallography, which is that the structure factor is the square root of the intensity. We all learned that in basics, and it is absolutely wrong. I don't know where these rumors come from. The reality of the situation is that it's proportional So there is a constant proportionality to the square of the structure factor. But that proportionality constant depends on resolution. It also depends on wavelength. It also depends on the polarization of the beam and the speed of rotation and where the spot actually falls on the detector. So you have to correct for all these things. Now, fortunately, all that math was done 100 years ago by a guy named Charles Darwin. That's him. It's not the Charles Darwin you're thinking of. That's the Origin of Species. Charles Darwin was his grandfather. Charles Galton Darwin was a student of Ernest Rutherford who worked with Henry Moseley to do a lot of the first X-ray measurements and derive the basic theory that we now use today. And Darwin's formula is a very, very useful thing for calculating the absolute intensity of spots. Problem is, when you're starting to think about stills, is this guy. This is the rotation speed of the crystal, which is 0. It's in the denominator, which means if you don't rotate your crystal, you get infinite spot intensities, right? Yeah, no, it doesn't work. So if I were to stress anything to John and my colleagues here is Darwin's formula does not apply to stills. It doesn't work at XFELs. And the problem is it's hard-coded in all the standard data processing packages for MX. So MOSFEM, XDS, Denso, none of them will work. Yeah, I think you probably wouldn't be here if you didn't know that. But that's the quandary. So what do we have to do? Well, it's tempting to think, why can't we just rotate the crystal? And it turns out you don't really need to rotate at the speed of light. It's not even close. But it is really fast. It's faster, actually, than the Voyager probe, which is the fastest thing that mankind's ever built. And given a 1 micron crystal rotating at the right velocity, you get a g-force, which is not quite enough to sever covalent bonds, but it is enough to break hydrogen bonds, just through the weight of the water atoms on the outside. So, yes, theoretically you could do this, but it's probably better to go back and maybe do a little bit of math. So the answer to that question is no, and perhaps it's time to ask the question, why do we like rotating crystals? Because there's advantages to not rotating them. In particular, many of you have heard this rumor that if you have a perfect nanocrystal, that the intensity is proportional to the square of the number of unit cells. That's true, but only for a still. If you integrate over it, it goes back to just being proportional again. That's where Darwin's formula comes from. So by not integrating over these things, by hitting the nail on the head and having the spots bigger than a pixel, then you can actually get intensities that are tremendously brighter than they should be if you were integrating over it, either by wavelength or by divergence or by rotating the crystal. So I actually predicted early on that we wouldn't see anything at the LCOS back in December 2010 because I wasn't accounting for this sort of thing. And I thought the background would be a lot higher. So what we really need to do is not use formulas from 100 years ago, but more like 150 years ago, which is Fraunhofer's formula. This is just the equation for scattering from a 3D grating. And Richard Carrion actually re-derived it more sensibly in his data processing paper. And this is actually the correct value. That's where the square comes from, right there. And everything in here is knowable. It's got a lot of the features of Darwin's formula because this is the equation that Darwin integrated over to derive Darwin's formula. It's the scattering from a single reciprocal lattice point. And it has the right units, photons per pixel, not photons per full spot. And I wrote a little program that implements this. I call it FastBrag because it's faster than another program I wrote. And it's been integrated into CCTVX. CCTVX.FastBrag is something that Nick Sutter has done. And the program is actually capable of doing single particle scattering as well. If you give it, if you calculate structure factors in a big unit cell, and then tell FastBrag the number of unit cells is 1, then it'll give you a continuous pattern, or if you give it an n number of unit cells, it'll interpolate the structure factors in between them. And it's useful for doing nanocrystal type stuff. If crystals get too big, then you need to start oversampling a lot. But it's good for nanocrystals. Now it turns out we can perhaps learn again from the past, because the people have done still diffraction before. This is the first paper to have done that. This is the structure of rock salt done by Bragg and a few of them, James and Balsabot. So the first crystal structure ever done. What they did is they didn't have a motor to turn their crystal. They had to run in and tweak it by hand. And so you didn't want to do that too often. So it's kind of like what we're doing at the XFELs. And they took a series of points and rocking one reflection through the Ewald sphere. Now, the important thing here, okay, they said, yeah, it would be preferable to have a continuous rotation, because Darwin had actually already derived the formulas for that. But what they did was actually really interesting. They compared everything to a reference spot. So they oriented the crystals so that I think it was the 300, was always on the Ewald sphere. And as you rotate the crystal about the axis going through the 300, it stays on the Ewald sphere. It doesn't change its partiality. And you rock the other crystal through it, and you compare the maximum intensity to the maximum intensity of 300, and that's your absolute reference. So that's your full and your partial, and they took the peak intensity as their fully recorded intensity. And that ratio is proportional to F squared. Remember, we don't really care what the absolute intensity is. We just want something that for one HKL versus another is proportional to the square of the structure factor. That's what we really want. We want an absolute, a general scale. And that's what the Braggs did. So if that's the right way to think about this, then we need to start thinking about partiality not as a volume, because a volume is something you do after you integrate. This isn't integrated yet. This is still. So instead of integrating over volume, we need to think about the surface of intersection between the reciprocal lattice point and the Ewald spheres. Now I've got 3 Ewald spheres here and 4 HKLs. And let's just say for the moment they all have the same structure factor. Now which do you think is brighter? Like F squared is always the same. Now this guy is mostly sticking out and not touching any Ewald spheres, whereas this guy is completely enveloped in them. Which one's going to, who thinks it's the top one? Who thinks it's the bottom one? Who doesn't care? Okay, it's all the same. Well, I hope to convince you with this of what that answer is. So this is now just taking those same circles of intersection for 3 Ewald spheres, say 3 wavelengths only, and moving them out so you can see them better. This guy is always hit. So it's 3, if you think about each wavelength coming in at different times, you've got, this spot never changes its intensity, and it's as big as it's ever going to get. So this is 3 wavelengths worth of intensity, whereas this guy up here is only touching 1 Ewald sphere, so it's a third of the intensity should be. So I hope this makes some sense. Before I've gone through a whole bunch more slides, but I think this one puts it in a nutshell. It's the volume of excitation is the wrong way to think about it. With stills, it's actually the area of intersection. You need to integrate that area, which could be more direct, but the way I'm doing it is through simulation, where I just calculate all the wavelengths individually, all the mosaic domains individually, and just add everything up. Which leads me to, okay, how do we know we're doing this right? Because what is the reference after all? Well, I think the best way to know you're doing something right is to cheat. And in particular, you can cheat with my fake data. So that FastBrag program, I've made a data set of 20,000 images from photosystem 1, just like the first data set, using the same detector parameters. The detector doesn't, the only differences are is the detector doesn't have any modules, it has no geometric errors, the wavelength's always the same, the sensitivity is always the same, the intensity is always the same. The only thing that's different is the orientation of the crystal. So if you ever had a chance of getting the structure factors right, this should be it. And I'd actually like to work with all you guys tomorrow to see if that's actually possible. And now Nadia and I worked with this a little bit in the past with some far-gone versions of XFEL. Now what you can do though is you can compare the right answer, since it's a simulation, you know what the right answer is, to what you get out the other end of the program. So now this red line is the Wilson plot of the right answer data, the ones I fed into the simulator. And that's one set of parameters. So it's kind of following it right, but it's noisy. So you can try something else. Well, this is taking max only. It's a nice straight Wilson plot, but it's the wrong B factor. That means the Lorentz factor is incorrect. It's tempting to accept this because it makes your high angle spots seem brighter, but what it really is just doing is sharpening the data, which you don't want to do. You want to recover the actual structure factors and do your sharpening after the fact. This is another thing you could do. I think that's not subtracting the background. And again, it's tempting to have lots of high angle stuff, but if you're suppressing your low angle stuff, you're going to see these weird maps where you've got waves running through real space. And eventually we found a good set of parameters where that seems to have some negative bias for the weakest data, but follows the right Wilson plot. And that's, I know a lot of you have gotten jaded about Wilson plots because they Well, because they're so telling about things that are wrong with your data. So we tend not to look at them anymore. But just to convince you a little bit, this is a Wilson plot from a synchrotron data set, which is not straight at all. But it was the best one that this particular group got. And they've never been able to refine the R and R for anything acceptable for publication. Now, by just applying a resolution-dependent scale to straighten it out, you throw that into our work, same parameters, you actually get a drop in more than 10% in R free, just from having the Wilson plot straight. Now, I don't recommend you try this arbitrarily. You need to do something that gives you the right Wilson plot to begin with. But if the Wilson plot's not straight, the Wilson plot being straight basically means the data is made of Gaussians. And all the atoms are modeled with Gaussians. So if the Wilson plot is non-Gaussian, then you're trying to fit all these Gaussian pegs into a non-Gaussian hole. And it will never fit very well. That's why B-factor refinement can be unstable. But if your Wilson plot looks good, that's your first indication that you've done things right. So another famous quote, which I think really is, in my mind, a reason for doing the simulations. It's really important to have a positive control, something you know what the right answer is before you go on trying to make a new discovery. Now, why do I believe FastBrag? Well, I believe FastBrag because it agrees with this other program I wrote called NearBrag. And NearBrag is the most assumption-free scattering you can do. So all it's doing is there's no Fourier transform, there's no unit cell, there's no concept of mosaic spread. The atoms are just points in space, which you list in a text file. You can have as many sources as you want, as many atoms as you want, and as many detectors. You can make the beam coherent or not coherent. All it does is measure the distance from the source to the atom to the pixel and count how many waves there are along that path. And this adds everything up on the detector. So it works in the near field, hence the name NearBrag. You can do crazy things like watch how Fourier transforms evolve, but it's particularly good at telling you what the total scattering should be no matter what. You can check diffuse scattering, you can do lots of different things with NearBrag. It's just really, really slow. So FastBrag is a way of shortcutting to the parallelepiped lattice. And so this, I get this same pattern out of NearBrag or FastBrag, same intensities. I make sure it's doing it right. So this is for a parallelepiped crystal, and you're seeing the interstitial interbrag peaks the way that you see them on the XFEL. Something I learned with NearBrag, though, is that if instead of making a parallelepiped array, a regular array, if you have the same unit cell but just rearrange those same atoms so that they are a spherical crystal, it looks like that. Same atoms, same unit cell, just different shape. So the shape transform, if it's round, kills all the interstitial Bragg spots, which might be why we haven't seen that many of them. So it's a shape-dependent effect. And something else I learned with NearBrag is this. This is now a two-dimensional crystal that I'm scanning through the beam. So effectively just redefining the unit cell. So when an atom gets too close to a unit cell here, I wrap it around to the other side. So same atoms, just redefining the definition of the unit cell. If you look at the diffraction pattern of this, you see the Bragg peaks, this is a false color image, never change. They're always the same on the Bragg peaks because the unit cell repeats the same. But the stuff in between completely changes depending on how you define your unit cell. It's a problem like, okay, you got lysozyme, and here's the diffraction pattern of a single particle lysozyme. But if you then cut it in half and move the unit cell by half, you get a kind of different looking pattern. So I think what's going on with diffuse scattering, at least the interstitial Bragg scattering, is you're not necessarily getting the molecular transform of the unit cell you think. You're getting the molecular transform of what's on the surface. So you're sampling really by holography the particles that are on the surface of this crystal. You don't really get any information about the bulk, but you do get information about how it ends. And that's where the interbrag spots come from. I thought that was worth mentioning. So radiation damage has been mentioned already. There's actually, unfortunately, not too much known about it at XFELs. But the most interesting result, I think, is the threshold of 100 femtoseconds, where things kind of don't fall apart until that point. Now, One way of explaining this that I prefer to think about radiation damage, because there's even argument about what dose means. Ollie and I have discussed that for a bit. I like to think of dose as being an energy-dependent thing. So just to put things on a scale that's familiar, this is, and it's in EVs, like we would talk about for particles. This is joules per mole, which, if you're a biochemist, you know what a kilojoule per mole is. And this is a phenomenon that's on that same scale. So 1 MeV photons are actually used for medical imaging. Our 10 keV photons are for crystallography. Sulfur and phosphorus K edges are on a keV water window. The very first chemical bond is a 10 eV, strongest chemical bond known as a carbon-carbon triple bond. So every event divides the energy of the incoming photon or quanta into smaller pieces. So you have a photoelectron and an excited atom, where the photoelectron bounces off of something and excites it. Everything is an energy division process, and it takes time. So you can think about dose as in joules per kilogram, but what is the energy of those quanta describing those joules? They take time to evolve down. So that's the way I like to think about it. It's just a concept. I've also gathered all the radiation damage data that I could find in the literature onto a single graph. This is the XFEL. This is all the room temperature data I could find. It kind of scatters a lot. So here I'm graphing the dose rate, as how rapidly the photons were thrown at the sample, versus the maximum tolerable dose based on the criteria of a particular paper. There's been one new point out here in no man's land. This was Andreas Maria Schmidt. That's a Lowy data point. So it does look like there is an upward trend if you go to higher and higher dose rates. But I think something that's really important to think about at XFEL is you have to be above this line. So if you can't do better than you can do cryo-cooled at a synchrotron, then you might as well do it at a synchrotron. So there is a significant advantage. I think we just saw a 33 gigaray one, so perhaps I need to add a new point up here. But this is just to put things in context of how radiation damage works and effects. Something else radiation damage does, and I can't stress this enough, is it introduces non-isomorphism. So we all know we can correct for radiation damage a bit by applying a scale factor and a B factor, but there's also always a residual non-isomorphism left over. This has been calibrated for MX under cryo at a synchrotron. It's about 1% per megagray, which is a good thing to bear in mind if you're trying to measure anomalous differences. You can't do, if you're trying to measure 1% difference, if you go for more than a megagray, you're already washing out your anomalous differences with radiation damage. What the non-isomorphism is for the damage mechanisms at XFEL is not clear. But it's definitely, I would be very surprised if it's so isotropic you can completely correct for it. There's going to be some residual, but that requires further study. But it is understood at synchrotrons. And that leads me into non-isomorphism itself. Now, Ollie's already talked about how to deal with non-isomorphism. I'm more concerned with how to prevent it. Because this is a problem that has plagued the field of MX since its beginnings. This is a paper where they actually used one crystal per photograph. They had radiation damage issues. They had isomorphism issues. And the way they dealt with it was by comparing to a reference data set of FCAL. As they were solving the structure, they kept going back and re-evolving it. This is the first macromolecular structure. This is from Kendrew's paper in 1960 for that thing. So the multi-crystal data collection strategy is not a new idea. It's actually older than the single crystal data collection strategy. So if they could do it, we should be able to figure out a way to do it now. So they used 22 photos, and they had to solve a 22 by 22 matrix on paper in order to solve the scales. But even then, scaling was really, really important. It was about 20 years later when it was finally figured out what was causing this, at least in a few situations. This is Magdoff and Crick. Some of you may know the Crick and Magdoff paper. This is the one that came before it, where they described the experiments that they did, not just the theory. And they divided errors into 3 categories. There's errors due to technical limitations, like your equipment. And even then, they were small. Much larger was a lack of isomorphism, which they described as difficult to avoid. And then there are slight changes in the vapor pressure surrounding the crystal, which we don't seem to worry that much about anymore, and maybe we should. because this is the last paper I'm aware of that really seriously looked into non-isomorphism and its origins. Later on, Louise Johnson actually pointed out to me that they had this problem with trying to solve the structure of lysozyme, the original structure of lysozyme. And I found in the literature, based on her guidance, the two PDB files that corresponded to this non-isomorphous trend. There's hundreds of them now, and structures represented in between. They're very close together. They're only 0.2 angstroms different, collected at two different relative humidities. But the R-ISO between those data sets is 44%. They are almost completely different for that change. And it's because the unit cell's resampling slightly, but even then, it took 50 years. No one really noticed that the unit cells were that different. What's going on in this case is the molecule is actually wobbling inside the unit cell. It doesn't change it that much, but it's a molecular motion in the unit cell that causes structure factors to change. And it's all due to less than a 10% change in the relative humidity surrounding all of the crystals. This is the letter that Louise sent me to describe this, where she said that they had this problem. They never did figure it out. They sorted the crystals and just collected on one of them. They called it type 2. That was the first structure of lysozyme. Type 1 came later. And she said they had this problem with crystals coming out of the same drop. But if you think about it, once you've opened your drop, and 2 minutes later when you mount your next crystal, is that really the same drop? It's probably changed a bit. So I equate this to physical properties. So if you're changing humidity, you're changing the volume of your crystal. But you're not changing the number of protein atoms in it. So that causes an elastic deformation. So every material has an elastic limit. So once it goes beyond that elastic limit, then you get what's called plastic failure, where unit cells will slide relative to other unit cells, and that's a permanent change. That's pore diffraction. Now, the vigorous hardness of lysozyme has been measured. That's the elastic limit, one way of measuring it, by poking something with a stick. And it was the lowest vigorous hardness ever measured. So these are very, very fragile things. So for the XFEL point of view, what to think about is, well, is there a humidity gradient here? Is the flow rate changing a bit? In a way, I think this is good news for XFELs in that, provided all these samples are in the same solution to begin with, they're probably at the same relative humidity, and all the other volatiles are probably the same. So we can expect to see better isomorphism with the type of sample delivery systems that we're using, hopefully. But it is something to definitely bear in mind. There's something else that happens, and I'll skip over the sample size argument, is temperature can have a big effect too. Now, everyone knows that tris buffer changes pH with temperature. Did you know that keeps going? So if you start out at 7, you go to 100 Kelvin, it's at 12. And this has been experimentally verified. So again, there's a temperature gradient here. So maybe think a bit more carefully when you're messing around with the jet. I also wanted to say one final thing about radiation damage, that we have, Ken Frankel there and I did an analysis of calculating the total radiation damage limit. So the total number of photons you can get out of a given HKL with a given structure factor. I won't walk you through this equation, but this is the analytic expression for how many photons you'll get at a given resolution. And I'll just tell you that the only things you plug into this are all knowable. And things like the molecular weight of the protein, you should know that. The size of your crystal. And most everything else is a fundamental constant of physics. This is calibrated for synchrotrons, but for XFELs, we know that there's a radiation damage advantage. So what you would do is plug in either the Nave-Hill coefficient or the H factor. Either one actually will do. The advantages from the radiation damage at the XFELs are proportional. So if you can get 10 times more gray calculated with rad dose, you get 10 times more photons. That's a proportional effect. Unfortunately, the B factor is in the exponent. So if your crystals are disordered, and you have that problem where you got really, really bright spots right around the beam stop, and then they just kind of dive into the background, theoretically, at least XFELs shouldn't fix that. Because even a factor of 10 isn't going to override e to the power of something. So but it does tell us how to pre-screen. If you can check stuff on a synchrotron, And you can see that all the spots are weak, low angle and high angle, and just be nice to get a longer exposure. That's where XFELs are really going to help with resolution. And that's the best I can say about resolution, actually, at this point, other than get better crystals. I do have a little web calculator that implements that equation if you didn't want to write it down. That's the URL up there. We'll show it again at the end. And it's also indicated in this paper. You just type in a few things you can get from a still. And actually, the resolution limit on a still is pretty well correlated to your V factor. But there are other ways, perhaps, to estimate that. So those are the things I mainly wanted to say here. This is where you can get this talk. This is where you can download my challenge data set. The points I'd like to hammer home is that I think we've got partiality backwards, at least for stills. It's counterintuitive how the spot intensities go. I also think everyone should be checking Wilson plots. And I'd like you to try my fake data set, and I think the B factor will be key for pre-screening for good results at XFELs. I see I've got plenty of time for questions. Michael?
I really enjoyed the background you gave. Very enjoyable to listen to. But can I go back to the Darwin formula? And there we have the rate of oscillation, omega.
Yes.
On the opposite side, on the bottom side, lower side, denominator. And the Lorentz factor, L, is numerator. Lorentz factor being a measure of the speed with which,
yes.
the time with which the reflection is in the sphere. So when you have a still, basically what omega equals to 0 and L equals to 0, and you get 0 over 0. That's why that equation doesn't work.
Yeah, I have some slides on that, which I didn't want to show. Maybe I'll walk through this.
We have time.
Yeah, I think we have time. So the Lorentz factor looks like a way to save Darwin's formula. And that comes from, if you have a reciprocal lattice point, it's d star away from the origin.
Right.
It spins around the spindle axis over some circle where that hits the Ewald sphere at diffracts. That distance is d, that distance is lambda. You can bisect this angle, and lambda equals 2d sine theta. Yeah. Right? Is everyone with me? Lambda equals 2d sine theta? Remember that? So that's never violated. But what does happen is the time it takes the spot to move through the Ewald sphere is different relative to what it would take if it were going straight through. So if you take the projection of the instantaneous speed of the spot, and just call that a speed, and then drop a perpendicular to the diffracted ray, which is the path that would be taken going straight through, the ratio of those two vectors is Lorentz factor. And that, there's a formula for it for normal geometry, and it can change if you have different geometries, but that's the Lorentz factor. And it does, in fact, approach, it's to the ratio of two speeds, and so they can be anything. So what we really should be doing is looking at the fact that Darwin's formula is for fully recorded spots, not necessarily partials. And that's where you hit this singularity. You should be able to rescue it then with the Green-O'Hellewell equation, which is the equation for how broad a spot is. It also has Lorentz factors in it. By combining these two equations, you still get yourself into trouble because it's then still an L over an L over an L, and then you're just left with omega.
So, you should also, I want to go to the place where you've got little clean circles that represent the spot at the reciprocal lattice point, and you make them into spheres or discs.
They're discs. Yeah.
Discs, okay. You've got to think about what happens when you think about the deviation of Black's law. You go a little bit away from the Black angle. What happens if the waves don't quite interfere with each other,
yes.
Instead of enhance each other? And as you go further away from the Black angle, not if it's completely away from, not if you've just got a fraction of a degree, but just a very small amount, then the intensity gets smaller. And so the reciprocal lattice point should really be related to how the waves interact with each other.
Yes, and that's what Fraunhofer's equation is. So that's, I did that before. So this equation
Yeah.
describes the intensity really over an area.
Yes, absolutely, yes.
At a pixel for a still image with one wavelength, one beam direction, and one mosaic domain, which has n unit cells
And
light.
important there for the size of the crystal.
Right. It's directly related to the size of the crystal. So then this is exactly what FastBrag does. Is for every pixel, I only evaluate it in the middle of the pixel. In order to get integrating sharp features over a pixel, you have to oversample and average it. But if you evaluate this function, this is a two-dimensional thing. It's a surface. So the pixels corresponding to the spot correspond to these little green disks. Now, if you replace this with a step function instead of a sync function, which is what it is, then you get those green spheres. But if you take these guys and slice them and say the full width at max, then that's what those green disks are. So assuming that the integrated intensity is related, the way it's done in FastBrag is the correct way, which is to actually evaluate the sync function. And I have another sync function for a sphere. But that's the way it's being done in that simulation. So that I'm confident is right. What I'm curious about is how the data processing responds to those images.
And what you're probably found is probably that we derived actually, and I found that in the equation in chapter 1 of James' book.
Yes. Yes, that's right.
For finite crystal. You also get that if the beam is smaller than one mosaic block.
Yes, you do.
You can have that in this field, so that's a tenth of light. Another way to handle these very small crystals where there's no mosaicity for either of those reasons is to treat them as single particles. And there's some interesting work you'll see coming from the ELSA group where they do that. Then what you're doing is using the concentration energy around the peak Bragg peaks as an alignment aid for a single molecule. You're using really Bragg to solve the alignment problem. But that then gives you a reconstruction of the whole nanocrystal, including the surface.
In fact, I would even argue that you could do this. So this is what you would call tachography, where you have a small beam walking over a crystal. Because it is the illuminated volume that's relevant, and the Fourier transform of that illuminated volume.
Exactly.
It turns out the sync function is the only one that has a neat solution.
Right.
All the other shapes they don't match very well. But you can do those with near Bragg.
I agree. I'll pay for the full transfer about that. One thing I didn't quite agree with you is if you have a complete number of unit cells,
Yes.
no half cells, then you'll get interference between the Bragg reflections. I'm not sure it tells you anything about the surface. It tells you about the surface if you have an additional half unit cell. You'll also have an interference if you have a complete cell.
But you have to remember the unit cell is something that we made up.
Right.
The crystals don't really care. So that they have something on their surface, and that seems to be what, at least based on this calculation, that's what the features you're seeing in the middle. I have other.
So as long as you have complete cells, the Bragg interference will be independent of the choice of unit cell.
Yes, as long as the termination on the surface is actually the end of a molecule, and that molecule is oriented the same way it is in the crystal, then yes, you should be able to phase from inter-Bragg spots. But if the surface is messed up, or if it's round, then it gets a lot harder. I got a whole bunch more slides on that. Maybe interested.
I think there are 3 pages on that topic.
Yeah, I think I'm on one of them actually. Okay. No more questions?
I have one.
Oh.
So if you go back to your movie where you showed that when you are throwing out the overloads, there's
Yeah.
not quite the plot. So are you throwing the overloads at random, or?
No, they're in order of intensity. So the beginning of the movie, the most intense spot was thrown out. And when you see the numbers 0, 1, 2, 3, that's how many of the top, how many spots I've thrown out. Just in ordering them by intensity, throwing out the most intense ones first.
Okay. And by doing that, you observe the changes on the whole map, on the whole asymmetric map.
So even though it's still 95% complete, the map looks terrible. That was a surprise to me when I first did that. Now, there's a saving grace in that if you use a program like Phoenix that fills in the holes, it will, in the map, the 2FOC map, substitute FCalc for the missing FOs, which can compensate for this effect somewhat. RefMech, I don't think, does that. So that's something that, and even Phoenix doing that is a controversial thing because it generates a lot of bias. But it always outputs the filled in and the non-filled in coefficients.
James, there's a very nice effect on this slide. If you look at the beginning, now you're going to start, as you take some out, you get holes in the tryptophan there.
Yeah.
But as you don't go along, it gets messy. And that's because the first overloads will be at low resolution.
Yes.
And then as you go further, you mess things up completely. But it's very nice.
Oh, thanks.
Are you throwing away actual overloads? Or
No,
just
the largest Fs. There's no diffraction pattern calculation going on.
So you were throwing those out, you weren't just taking their magnitude?
Yeah, just throwing them out entirely.
Okay, because another way would be to say saturating, you sort of squash your dynamic range, which is probably what's happening in the XFEL data processing. If you've got an overloaded pixel and you throw it out,
Yes.
you're effectively reducing the intensity of that input.
Overloads, they're big things. They're very important.
Yeah, well, okay.
Sorry, Michael, we throw out overloads these days.
Well, you can solve the data with bright, medium, weak.
You can do it if you're Lawrence Bragg. See, he solves the structure of ice by deduction. Say, okay, this one's bigger than that, so therefore water atom has to be over there. And that was the first phasing, by deduction.
You can very easily play with the overload level of this one.
But it's definitely the case that, yes, you will get a similar effect from bias. If your pattern is very nonlinear and you've taken your brighter spots and made them smaller, then yeah, you'll see the sum really of this with that first image.
Tom, White, would you agree that for some data sets, real data sets, throwing out overloads improve things, and for others keeping them improve things?
I think so, yes.
Okay. That's,
Well, that was
no,
on
we're just telling you what we observed.
So, well, throwing out overloads is okay if you have something else. And this is the problem, is if you have, the reason why we throw out overloads, we tend to throw out overloads in MX in general, is because they really screw up scaling. So if you have an overload that's not flagged as an overload, then the scaling will never converge on the right values. And so only by ignoring overloads can you get good scaling. But then, yeah, if it's the best observation you've got, it's better than nothing. But unless you're interested in bio differences.
Actually, when you do profile physics, you can get the value of the overloads. You do not do the d-squared fit for those pixels which are overloaded, but you still get the slope of the profile. And so you get a pretty good idea what the value of the overload would be when you do profile fitting properly.
Yes. That is a feature in Moslem and in Denso. Not sure what XDS does. Yeah, I'm sorry to say, I'm pretty sure the defaults right now are that feature's turned off.
There's a confounding factor here, which is with the CS pad, has some strange non-linear behavior as you go to overload. And we don't really, well, I don't know if it's just us that haven't understood what the
module go insensitive.
Yeah.
The first crystal I ever saw, I looked at the overload reflections, and they gave me planes which are important. I knew those for the atoms. So just by looking at the overloads, I could solve the structure.
Can I ask, in conventional crystallography, what's a typical low resolution cutoff? Yeah, like, I mean, how big is your
beam stuff?
Yeah.
Yeah,
Maybe 70.
Make the beam stuff as small as possible.
A lot of programs cut it at 50. And
Right, well, I just wonder
that's
whether...
because there's a Denso file floating around somewhere that has 50 as the level.
Depends on the beam stuff.
I know.
Yeah, it depends on the shadow of the beam stop, so you don't throw out anything in traditional crystal. If you can. But there's the beam stop and the shadow, and you scoop everything.
It is true that there once was a time, not so long ago, when 6 angstroms was the low angle cutoff, because that was the days before bulk solvent corrections. And without bulk solvent, low angle stuff just goes crazy. And so a lot of historical R factors are calculated from 6 on out, because that gets too high if you go lower. But after the Tronron revolution, I think we go down to about 50. Some will go lower, some won't.
But I probably people don't know here that Max Baruch actually helped to solve the structure of hemoglobin by looking at the solvent changes in the low evolution structures.
I read his account on that, and he said he had this, he worked on it for a number of years until this snot-nosed graduate student named Francis Crick joined the lab and told him that wasn't going to, explained to him how it wasn't going to work. But he never did explain why it wasn't going to work, so I wonder what that is.
The solvent changes in quality work. Because that gave him the outline of the molecule. That worked.
Okay.
So is there a way to explain site-specific modification of the electron density to overload? Because also to show that it happens in the whole class.
The only site-specific nature of it would be these peaks and valleys from the missing HKLs. So if you have a very strong and low, for example, the 001 will lift the left half of the unit cell and lower the right half, depending on which phase it should have had, and if it's a very bright spot. So you get more site-specific stuff if you have, well, actually, like Michael was saying, if you have a very strong feature, it can actually dominate the intensities in the pattern. And you can, if you have a strong heavy atom, you'll see the Fourier transform of that atom in the data, and that could bias the overloads. And I'm just kind of guessing at that. Does that make sense to you?
Can I add one more question? When you mentioned, I don't remember what that thing was, that changes pH due to temperature.
Tris.
Right.
Tris ruins everything.
How quickly would the pH change? Like if we have a really fast flow rate, yes, it evaporates very quickly, cools very quickly, but will the pH have time to change? Will that?
Yes. Yeah.
Really?
It's probably nanoseconds. Because it's as fast as a proton can equilibrate off and onto a tris, so, which is pretty fast, I think. I don't think it's been measured, but I imagine that's pretty fast. It's not femtoseconds, but microseconds, yeah, I think it's probably done by then.
So nano or micro?
I'd say micro. Micro's safe.
You can look it up for any chemical reaction, maybe not for tris, but for acetic acid or whatever.
Okay.
Or you can just not use tris.
You can change pH by changing distance along the jet.
Yeah.